Welcome to the 9.3, 9.4 notes. This will be the final section of notes for this school year. So I wanted to start out by saying that this notes packet follows from the activity that we did in class. So if for any reason you missed that activity or part of it, please go back and watch the class recording first, because I'm going to assume that you have the knowledge of what we discussed in class, okay? So this section is about exponential functions. This is a potentially new type of function. So I wanted to start by talking about how it's related to functions that we've already discussed, namely polynomials. So recall that a polynomial is the sum of terms in which all variables are raised to exponents that are positive integers. So that's just a fancy way of saying that a polynomial is the things that we've been working with all year, where our exponents are non-negative and non-fractions. Okay, so some examples of polynomials are 2x squared, for example, is a polynomial. That would be a monomial, one term. We have something like 4x plus 3 is a polynomial. 15 is a polynomial. We can have 7x cubed plus 1/2 x minus 4 is a polynomial. Now, even though there's a fraction, because the fraction is a number, that's okay. We can't have any variables that are in the denominators, and we can't have any variables with negative exponents, because that would mean that we have a variable in a denominator, okay? So those are the rules for polynomials. That's no square roots, no variables in denominators, no variables with negative exponents, and no variables with fraction exponents, right? So fraction exponents or radicals, negative exponents or fractions, okay? So those are polynomials, as we've been using for throughout the year. The new type of function is called an exponential function. And an exponential function has the form f of x equals b to the x, okay, where b is a number and x is a variable. So the variable, notice now, is in the exponent. Before, our variables were bases. All of our variables were the base raised to a power or raised to no power, which would be 1. Now, the base is a number and the exponent is a variable. So examples of exponential functions could be, instead of 2x squared, it could be 2 to the x, for example. Okay, so this is an example of a polynomial where your x is the base and 2 is the power. The exponential function has 2 as the base and x as the power. Because x is a power, it's an exponential function. Okay, if we had 4 to the x, that's an exponential function. We can have a number raised to an exponent. We could have something like 4 to the 3x because we still have a variable in the exponent. So what is it that makes a function exponential? It has a variable in the exponent. Variable in the exponent. Okay? More examples. We could have something like 7 to the x plus 2. We could have negative 3 to the negative x. Okay? So this time we can have negatives in our exponent because we have still a variable in our exponent. Okay? So kind of take a look at these examples that we've gone through and then see if you can do the try this, where you're selecting the functions that are exponential. So you're circling the functions that are exponential. Okay, so if we look at these, part A, we have x to the third. My exponent does not have a variable, so this is not exponential. Part B, we're looking at this, it's 2/3 to the x. Variable is an exponent, so this is an exponential function. Circle. Part C, 5 to the x minus 2. Variable is in the exponent, so this is an exponential function. And then 2x to the fifth, the exponent does not have a variable, so this is not an exponential function. So your answer should be B and C only. Let's take a look at example 1. So now that we can identify exponential functions, what do they look like? And we're doing kind of a shortened version of this section, which is why we're combining sections 3 and 4. And we're just going to look at what these functions look like by using your calculator. So if you need your graphing calculator, go ahead and pause the video to go grab your calculator. Okay. So on the calculator, we're going to go into the y equals. This is in the top right corner of the calculator. Y equals. We're going to go into y equals, and we're going to type our first function as y1. So this is the same as saying something like f of x equals 2 to the x, and I wanted to graph it. Then I would set y1 in the calculator equal to base 2 raised to the power is this little caret underneath clear, raised to the power of x, but we want to use x, the variable. So we're going to do this button right up here in the top right underneath mode. And so now your calculator should show you 2 raised to the x. If you have a newer calculator, it might have put that x actually in as an exponent. Okay? And now what we want to do is I'm going to have you do zoom and set it to this standard zoom. So we're going to go down to number 6 and hit enter. And that way I just know we're all looking at the same screen. This is a 10 by 10 by 10 by 10 grid. Okay, so now when I'm looking at this graph, notice it seems to disappear, and then it comes from the negative x-axis and it raises really, really quickly. Actually, this is even faster than a parabola, this change in an exponential function. And so to graph it, and we're just going to sketch a graph, we're going to plot a couple of points. So how do we find the points to plot? Well, above the button that says graph, see how it says table in blue. So I'm going to hit the blue button, which is second, and then I hit graph. And what that will do is it will show me a table of values. So it'll give me a couple of points to plot. And I'm going to plot the point 0, 1, 0, 1. And I'll plot the point 1, 2, 1, 2. And maybe we can do one more, 2, 4, 2, 4. And then we want to see something that's going kind of off to the left, something in quadrant 2. So if you press the up button, it will take you to when x is negative 1, y is a half, 0.5, 1 half. So when x is negative 1, y is 1 half. Okay. Now, what's actually happening is the function doesn't disappear like it appeared to do in our graph. See how it looks like it disappears? What's actually happening is that those values get so close to the x-axis that they stop being distinct from the x-axis. So this line actually kind of blends in with the x-axis. So the way we graph that, we're just going to graph this so that it kind of goes right along that x-axis. And then this goes up through those points, and it keeps going, and it keeps getting steeper and steeper. And that is 2 to the x. Now this graph should look familiar. It should be very similar to the graph of the number of zombies created in the worksheet that we did in class. Okay. Now we also want to compare this to the function 5 raised to the x power. So we're going to go back into that y equals menu. And then instead of replacing the equation, we're going to go down to y2. And we're going to type 5 raised to the x. So now it should show 5 raised to the x. We don't have to change the window because we already did that when we graphed our first function. So our window is the same. So when I hit graph, it'll be on the same grid. And notice the new one, the new graph, goes up even steeper than before. So when we go into the table, so second table, we're going to look not at y1, but at our y2 values. So notice we still have when x is 0, y is 1. So that point stays the same. But now when x is 1, y is 5. So our next point is 1, 2, 3, 4, 5, 1, 5. And then if we tried to go up again, we would get when x is 2, y is 25, which is way up outside of our graph. And so the way we can do this is we can just say that goes up very steeply, so steeply that it never even hits x equal 2 on the part that we see on our paper. And then what happens in the negative values, well now when x is -1, y is 0.2, which is 1/5. Okay, so hopefully you're starting to see some patterns with these graphs. So let's talk about what is the difference between these two functions, 2 to the x and 5 to the x. Okay, well, we can see that they both kind of go out along the x-axis here. And they both grow very steeply, right? So they both have significant rates of change. So we can say both graphs extend along the negative x-axis. Both grow very quickly. And remember, that's a property of exponential functions that we talked about in class. But one of the differences is that 2 to the x, that was this one, grows less quickly than 5 to the x. Grows more slowly. I'm not sure if that's the proper English, but 5 to the x grows even faster than 2 to the x. And notice that has to do with the base. So the smaller the base is, the kind of less steep the graph will be. Okay, but in example 2, we're asking kind of a very similar question, except now we're looking at with fractions. So in example 2, let me recenter this on the page. In example 2, we're looking at what happens now if I have 1/2 raised to the x and 1/5 raised to the x. So again, we're going to look at this in our calculators, but I want you to pause for a second and think about what do you think will happen? And then let's look at it in our calculator. So we're going to go back into y equals, and now we're going to raise 1/2. Now it's important to have parentheses, 1/2 raised to the x, because I'm not just raising the 2 to the x, not just the denominator, I'm raising the whole 1/2 to the x. And we want to make sure that that's very clear for our calculator. And the second equation we're going to look at is raising 1/5 to the x power. So I'm going to go ahead and type both of them in here. We're going to go ahead and graph it still in the standard screen, in the standard window. And that's the first one we graphed, which was 1/2 raised to the x. And there's the second one we graphed, which was 1/5 raised to the x. Okay, so what do you notice about these graphs? If you look at the one that we drew earlier, and you look at the one that we just graphed, there's some similarities, but there are definitely some differences, right? They look like mirror images of each other, and they actually are mirror images of each other. And we can see this by going into the table of values. So remember, y1 was the 1/2 raised to the x. So we have these points. We still have 0, 1, but now we have 1, 1/2. 1, 1/2. These are all very small, so let's find other points that are easier to plot, such as -1, 2, -1, 2, and -2, 4, -2, 4. Now notice these are very similar points to what we plotted up here, except on the opposite side of the x-axis. So this is a reflection, kind of like the project that we did where we folded the paper. And so if we draw this graph, it's very similar, but backwards from our 2 to the x graph. And the same thing's going to happen for 1/5 to the x. We still have the point 0, 1, and now we have the point 1, 1/5, 1, 1/5, which makes our graph even closer to the x-axis. And then we have the point -1, 5, -1, 2, 3, 4, 5. And we're looking in the y2 column because we're looking at the equation for y2. So we look at -1, -1, the y value for the second function is 5. When x is -2, the y value for the second function is 25. That should sound familiar because those are the same values that we got for the last graphs that we functioned, or last functions that we graphed. Okay, so again, we want to compare these. But now, notice the graphs are decreasing very rapidly. So now we can say both graphs extend along the positive x-axis. Both decrease very rapidly. And we can say 1/2 to the x decreases less rapidly than 1/5 to the x. 1/5 to the x slows down faster than 1/2 to the x. Okay, now why would these two graphs be opposites? Let's look at where they come from, right? 2 to the x and 1/2 to the x. Well, 2 and 1/2 have a very special relationship. They're reciprocals, which means that I can rewrite 1/2 in terms of a base 2. So remember, if I wanted to write 1/2, I can rewrite it as 2 to the -1. And therefore, I can rewrite this function. I can replace the 1/2 with 2 to the -1 raised to the x. And that means using the power rule, power to a power, I multiply the exponents, so this becomes 2 to the -x. So these two functions have the same base, but opposite exponents. So for a positive x here, you'll have the same value as the -x here. And that is why we have that kind of flipping, that reflection going on between these two graphs. And we can do the same thing for this one. We can say the 1/5 is really 5 to the -1 raised to the x, so it's 5 to the -x. And that's why we have this reflection, okay? So I have the properties summarized here in the table below. For an exponential function with a positive base, where our base is not 1. So why do we care that our base is not 1? Well, what happens if our base is 1? 1 to the x power. Let's look at if I have 1 to the 0 power is 1. Anything to the 0 power is 1. 1 to the first power, 1. 1 to the second power, 1. 1 to the third power, 1. So that will happen for any positive number. What about a negative number? 1 to the -2. Well, that's 1 over 1 squared, and 1 squared is 1. So that's also 1. So 1 to any power, 1 to any power is just 1. That's why we say we don't care when the base is 1. Okay, it doesn't behave like an exponential function when the base is 1. So all of those properties that we just talked about, okay, if we do the horizontal and vertical line test on these functions, we'll find that they are 1-to-1. And that's important for as you progress through classes, like for example, in pre-calculus, we're gonna talk about why it's so important that exponential functions are 1-to-1. Okay, all of our functions had a y-intercept of 0, 1. None of our functions that we just graphed had an x-intercept. They all continued forever in both directions. Even though it grows very fast, it keeps going and going and going and going, and it never stops. Therefore, its domain is from -infinity to infinity. And the entire graph was above the x-axis, and therefore the range is from 0 to infinity. So those are some of the properties of these exponential functions. Looking over at the next page, for example 3, this will not be on any assessment for this class, but I think it's important for you to see kind of the more algebraic side of these exponential functions, since this is an algebraic class. So exponential functions can be solved. Now, we can right now only solve some of the more basic exponential functions because we're limited with our ability to compute such large functions right now. So I want to show you 3 examples on how you can solve these functions. However, this won't be tested. Okay, so in our first example, we want to know what x equals, and we have 2 raised to the x equals 16. Now, the trick for solving this type of function is to see if you can write both sides with the same base. So remember, base is the number that holds up the exponent. Like the base of the table is the legs of the table. It's holding up the tabletop. The base of this is the part that's holding up the exponent. So the question is, can I rewrite this with a base of 2? In other words, is 16 a perfect power of 2? Well, 2 times 2 is 4, times 2 is 8, times 2 is 16. So we have 2 to the 4th is 16. So 2 to the x equals 2 to the 4th. And if the bases are the same, then their exponents must also be the same. And that's the big rule for how to solve these exponential functions. And therefore, x equals 4. Let's see if we can do the same thing here. Now, I have a base of 9, 9 to the x. Can I write 27 with a base of 9? Well, we have 9, and then we skip right to 81, so that doesn't work. Well, can I rewrite 9 with a different base? Well, 9 I know is 3 squared, so let's try that. We'll rewrite this as 3 squared to the x. And so now I want to write 27 as a power of 3. So we have 3, and then 9, and then 27. So 27 is 3 to the 3rd. Now using the power rule again, we can rewrite this as 3 to the 2x equals 3 cubed. Same base, then their exponents must be equal. So we have that 2x equals 3. Divide both sides by 2, and x equals 3 halves. Okay, so again, the trick for solving these functions is to get the same base so that you can set the exponents equal to each other. So let's look at this example. 4 is my smaller number, and so I want to know, can I write 8 as a power of 4? 4 and then squared would be 16, so that didn't work. Then I ask, can 4 be written as a smaller base? Well, 4 is actually 2 squared. So we'll rewrite this, 2 squared to the x plus 3 equals, can 8 be written as a power of 2? 2 times 2 is 4, times 2 is 8. So I know that 8 is 2 cubed. So this is 2 cubed to the x. And then using our exponent rules, 2 times 2x, got to distribute that 2x plus 6 equals 2 to the 3x. The bases are the same, and so the exponents are equal. So I can set 2x plus 6 equal to 3x, subtract 2x, 6 equals x. Okay, again, it won't be assessed, but it's still important for you to kind of see that and start understanding it so that next time you see exponential functions, it will come more easily. Okay, now the last topic that we're going to talk about is, what if my population, my initial population, is not 1? Okay, so if you think back to the zombie worksheet that we did, the initial population was 5. And therefore, even though the pattern was multiplying by 4 over and over and over again, we still had to multiply by a factor of 5. And that's more realistic than having kind of these simple exponential functions. We usually have a slightly more complicated exponential function. Okay, so up till this point, what we've done in the notes was a starting population of 1. So really, if we're looking at 2 to the x, it's 1 times 2 to the x. And therefore, we can break down a new function where we have that y equals c times the quantity of 1 plus r to the x. So what are these variables? Well, y is the total population. So that would be the total number of zombies. Okay, it could be the total population of bacteria. It could be the total number of atoms. For example, this can be used for decomposing of atoms. So carbon dating uses this type of function. Okay, so the total population. C is the initial population, or it's what we started with. What we started with. Okay, R is the rate of change. Rate of change. That's how fast is the population changing. And then X is the amount of time. Now the variables are also described in the print here, okay? But I think it's nice to have a visual representation of what those variables mean. So let's see if we can apply this. In example 4, okay, we're starting with a town called Jackson with a population of 15,500. That is the starting population, right? So that's going to tell me immediately, I'm thinking, okay, that's my starting population. It was consistently increasing by 10% per year. That's important, 10% per year. That's a rate of change, okay? And if this yearly increase continues, predict the city's population in 2025. Okay, so I have underlined what I think are the important details. Okay, so then I'm going to go back. I'm going to start with the equation y equals c times 1 plus r to the x. And I'm going to say, what do I need to define? I need y, c, r, and x. Okay, I would like to know, predict the city's population in 2025. So the question that's being asked is, what is y? What is my final population? Okay, so y equals population in 2025. Do I know C? Well, C, remember, is my starting population, and I do know my starting population was 15,500. R is the rate of change. How fast is this population changing? And that's given here, 10% per year. 10%, which is 0.10. And then X, which is our amount of time, how long is this happening? And this is one that we have to look in at the question more carefully. Okay, the starting population was in 2005. My ending population is in 2025. So how long has the population grown? Well, if we go from 2005 to 2025, I can say that's 20 years. Algebraically, we calculate that as 2025 minus 2005 gives us 20. So X is 20 years. So I'm going to start substituting into this function. Y equals 15,500 times 1 plus 0.10 raised to the 20th power. Simplifying, I can complete the operation that's in the parentheses. 15,500 times 1.10 raised to the 20th power. From here, I'd put it into a calculator. So I'm going to do 15500 times, put it under here, times 1.10 raised to the 20th power. Now it's important that it's only the 1.10 that's raised to the 20th power. You do not want to group together the 15,500 with the 1.10. Order of operations says we have to take care of that exponent first. We cannot multiply these together first. And so we end up with y equals 104,276.2492. And what does this number represent? This number is a population. Well, if I'm thinking about a population, I cannot have 0.2492 of a person in my population. And so I can say 104,276, 2 rounds down, people. Okay, the next question is very, very similar. Okay, I'd like you to try it on your own, and then we'll go over it together. Okay, so we want to write an equation that models an initial population of 10 mice that grows at a rate of 20% every month, and we want to find the population of mice after 8 months. This is a population problem, so I know I'm going to use that exponential equation, y equals c times 1 plus r to the x. I need y, c, r, and x. Which one am I asking for? What is the population after? The population after is y. So this is population after 8 months. Okay, what is C? C is our starting population. So where is our starting population here? Initial population is 10. 10 mice. R stands for rate. So what rate are we at? We're at a rate of 20%. 20% is 0.20. And then X is time. How long? And that's our 8 months. 8 months. And so we substitute them into the equation. Y equals 10 times 1 plus 0.20 raised to the 8th. Notice my rate is in months and my time is in months. Just like in the previous problem, my rate was in years and my time was in years. That is important. Okay, so this was the first part of the question, was to write the equation, and then we want to find the population, so we want to compute this as well. 10 times 1.2 to the 8th. From here, I'll go to the calculator. 10 times 1.2 raised to, remember that raised to the button, raised to the 8th. 42.998. 42.998. Again, this is a number of mice, and so we're going to round to 43 mice after 8 months. Okay, I'd like you to look back through the notes and then write your summary for this section, and we'll go over any questions you have in class.